Hello Year 13 chemists, welcome to TP's Chemistry Cuts. In this clip we look at what indicators are, how they work and how we use a pKa value to select the correct indicator for a given titration.
This is the last piece in the titration curve jigsaw, if you like, and it's how indicators work and why we need to be careful which indicator we're using for a particular titration. Okay. So first off, to remind you that indicators are in fact mostly natural products that we find in nature. They're quite complicated in terms of structure, so we don't really need to learn what they look like. They are weak acids, and importantly the weak acid is a different colour to its conjugate base. So if we look at methyl orange, which is a classic example, if you put that into water, okay, it is a weak acid, so it generates H3O+. Its conjugate base is this, so I've just used a simplified abbreviation for it. Methyl orange itself is red, and its conjugate base is yellow. And generally, in solution, you get a mixture of the two, so it has an orangish colour, and hence its name. Now, before we actually go into how indicators work, it's really important you understand and are able to discuss the equilibrium principles about moving backwards and forwards in this reversible reaction. So if you add acid, remember it's this that you're actually affecting, so that increases and you lose equilibrium. So the system responds by favouring the reverse reaction to try and reduce that. This reduces the concentration of this and increases the concentration of that. So overall, the effect of adding acid is to diminish the yellow and increase the red. So if you add enough acid, it just goes red. Okay? If you add base, on the other hand, you're removing that, so you're reducing the concentration of it, and so the system responds by favouring the forward reaction. Okay, so the concentration of methyl orange itself, the red part of it, goes down, whereas the concentration of its conjugate base goes up, and so the yellow colour intensifies at the expense of the red. So if you add enough base, then it goes yellow. And what you'll find is if you have a red solution, a pH change of 2 pH units will move it right the way across from red to yellow. And that's the important point. 2 pH units will move it from one extreme to the other. Now what I've done is I'm taking a nice, easy, strong acid, strong base example. And what we need to look at is the pKa of, say, this indicator. So the pKa for methyl orange is 5.3. So if the pH of the solution in which methyl orange is sitting is 5.3, what does that tell you about the concentrations of these two? This is something we've covered in the titration curve. If the actual solution is 5.3, in other words, the pKa of methyl orange, what can we say about methyl orange and its conjugate base? They have equal concentrations. So if you like, if we're talking in terms of a position, it's right in the middle. Okay. Now, although it doesn't fit here, what would happen if that was here in the midpoint, the equivalence point? Okay. So if I was to put it there, say that was 5.3. Okay, use your imagination a bit here. So if I go one way, I just need to go 1 pH up, because remember, it only takes 2 to go from one extreme to the other. If you're in the middle, it takes 1 pH to go one way completely, and 1 pH to go the other. Okay? So if I go up 1, so that would be here, and down 1, that's the range. Here, down below here, okay, this is where you are at the extreme where you've got a lot of acid. Okay? And we said if you add acid, it drives it that way. So it's going to be red here. Okay? Here you've got a lot of base. It's got too much base. It's gone to the other extreme, and it's going yellow. Okay? And in between, that's where you've got a mixture of the two. Now, so you're doing this titration. So you forget this for a minute. You're doing a titration, and you're adding your base. You get to this point. How much base will it take to go from there to there? Usually about 1 or 2 drops. So when you add 1 drop, it suddenly increases the pH by several orders of magnitude, or several points. So you go straight through this, you go from red to yellow. And that's how the pH, the indicator works. It's because you're putting it as close, its pKa value, you're selecting it because its pKa value is as close to the equivalence point as possible, and it's because the equivalence point is the point at which where it's in the middle of the biggest pH change for the smallest addition of either acid or base. And that's the critical thing. You add 1 drop and you get a very large pH change. And so if you've got the pKa right in the middle of that curve, what you're doing is you're starting at one extreme, adding 1 drop, you've got 2 pH change, or 4 or 5, even more, and it's going right the way across to the other, and bang, the colour changes. And that's how it works. Okay? It's as simple as that. Now, if you pick the wrong indicator, say your pKa is too low, say that this was 5.3, but we picked an indicator where its pKa was maybe 3, so it was down here, okay, then if we looked at our range, it would be like this. Okay, so if we've got a pKa, say, e.g. 3.5, what's happened is you're doing the titration, you've gone through, it's changed colour. When you get to here, it's too late. You've gone through, you haven't got to the equivalence point yet. So it's changed colour and you've not got to the equivalence point. Is it particularly useful? Because you've got a pH change of 2 here, not at the massive change up here. You can get to other things, like alizarin yellow. If you were to select it here, which has got a pH up of around here, okay, pKa, sorry, what's happened in this second one here is you've done your titration, you've gone past the equivalence point, and it hasn't changed colour yet. It's still the first colour. So you've added too much by the time this has changed colour. So what you've got to do is pick an indicator whose pKa is close to the equivalence point as possible, because that's where you get your big change in pH, and that's sitting at the right point where you're going to change it so it changes the colour of the indicator. Yes?
So would you use that that last one where it had a pKa of 11? Would you use that indicator for something where it was like a weak acid titrated to a strong base?
Yes.
Because the equivalence
point's higher. So things with low pKa's you would use in a titration where you've got a weak base, because the weak base has got a low equivalence point because it's forming the conjugate acid, so you need the equivalence point to be somewhat, or the equivalent point is less, so you need a pKa that's lower. So what you'll find is phenolphthalein, for example, is great for strong acid, strong base, because its pKa sits right in the middle of that curve. If you use that with a weak acid, however, where you've got a higher value because it's forming a conjugate base, then what you'll find is it changes colour too early, because it's changed colour down here, and in fact you want it up here somewhere. So the type of question you'll be asked is, you'll be given 3 indicators, is to plot something like this. Put their pKa on the titration curve, go plus and minus 1 above and below, and see if that range is anywhere near the equivalence point. If it's too low, then you've gone through the range. It changes from one colour to the other, the pH of 2, before you get to the equivalence point. If you've got a pKa too high, then you've gone past the equivalence point with the big change, but it's still not going to be enough to change the pH, the colour of the indicator.
How do you know it's gone too far?
So what you'd be expected to do is to say which one would be a suitable one for this this titration, and say why. And you'd say the reason is because its pKa is very close to the equivalence, or it's the closest to the equivalence point, and so it's at that point one drop will change a big change in pH, which will cause the indicator to go from one extreme to the other. Okay, so what we're looking at is a scenario where the pKa of the indicator is very close to or on the pH of the end point. So what you're doing is mapping 2 things onto each other. What that tells you is that you've got a 50-50 mixture of the indicator and its conjugate base in the solution on the end point. If you're slightly before the end point, addition of 1 drop of, say, base will cause a large pH change. Okay? And so that means you will drive that equilibrium from one end right the way to the other. Because that's what it says up there, isn't it? 2 pH. Well, we're going to have a change of at least 4. So what we're saying then is that if we're just here, you've got a relatively low pH. So you're doing the titration, you're just before the equivalence point. And it's worth emphasising that you're just before the equivalence point, then your pH is quite low. You then only add 1 drop, and what that does is it takes you right up the vertical section. And so you get a very large change in pH for a tiny addition of base. And that's enough to drive this equilibrium from this extreme across to that extreme. It only takes 2. We've gone probably 4 or more. And so the indicator will change colour as you've passed the equivalence point. If you've got the pKa too low, you'll go past the change in colour, because going around this section here is enough to take you through 2 pHs. So it will take you through the pH range enough to drive that equilibrium from one extreme to the other, but you've not yet reached the equivalence point, so it changes colour too early. If you have it too high, then it will go through the big pH change too late, because the pKa, where you've got 50-50 mixtures right up here, you need the pH change to be up here somewhere. And so you'll go past the equivalence point, it will still be the original colour, and so the pH change, which will cause the colour change, is too late. You've got too much volume added. Okay, so it's not worked properly.